Dear students, in this video we are going to see a degree sequence and Eulerian graph. Now, see what is degree sequence of a graph? Degree sequence of a graph is the sequence of the degrees of the vertices listed in non-increasing order, that is largest to smallest. You see this example. Now, what is the degree of E? 4. Degree of F? 4. Degree of G? 1. Degree of D? 0. Degree of C? 3. Degree of B? 4. Degree of A? 2. Now, we have to write the degrees. We have to write the degrees from largest to smallest. That is here. For example, 4, 4, 4, 3, 2, 1, 0. That is the order. That is the sequence. That is the degree sequence. Okay, now you see here why we write here degree is 0 of this particular vertex, because no edge is incident with this vertex. That is, you can say another way, no line is from this vertex to another vertex. No line, no edge. That's why degree is 0. That's it. Now we see what is a path and cycle. Now, what is path? A sequence of distinct vertices such that two consecutive vertices are adjacent. For example, you see A, D, C, B, E. That is A, D, C, B, E. A sequence of distinct vertices. We have to list the vertices. We have to list all the, not all. We have to list all the vertices such that two consecutive vertices are adjacent. For example, here A and D adjacent, so that you can write A, D, then C, then B, then E. In another way also you can write a path. Now this is called a path. Now what is this? Is not a path, it is a walk. This one. Why? Because here you can repeat the same vertex, but here you cannot repeat, because path means a sequence of distinct vertices. Path means a sequence of distinct vertices. Here vertex A is not repeating anywhere in this path, but you see here this vertex B is repeating, D is repeating, E is repeating. So this is not a path, but it is a walk. This one. Now what is cycle? Cycle means a closed path. Now you see this is a path. When you start from the particular vertex, after completing all the vertices, if you come back to the same vertex, that is called a cycle. You see, this is A, starting vertex. Now you see, after E, this is a path. After E, you write the starting vertex. This is called a cycle. So cycle means a closed path. Now what is a trail? A walk with no repeated edge. You see here, this is a walk. A, B, E, D, C, B, E, D. These all are vertices. Now here B, E. What is B, E? B, E is an edge. See, the edge is repeating here, but this is a walk. Walk means edge is repeating, not path, and edge is also repeating. That is walk. But what is trail? A walk with no repeated edge. This repetition of the edge is not allowed in the trail. That's it. Now, what is connected is disconnected. What is connected graph? What is disconnected graph? Now you see, a graph is connected if there is a path between any two vertices of the graph. Now you see here, suppose you take the vertex B and E, definitely you can find one path. But you see this graph, this is called disconnected. Suppose you take C and E, can you find the path from C to E? No, because here from E to this part, or from F to this part, there is no edge. That's why here we cannot find a path. The connected means a graph is connected if there is a path. You can find a path between any two vertices. Whatever vertex, whatever a set of vertex means two vertices, this and this, or this and this, means B, E, C, E, A, E, like if you take any two vertices, then there is a path between the two vertices, then we can say connected. So this graph is connected, this graph is not connected. Now we can see this theorem. Okay, what it says: a connected multigraph has an Euler circuit. This is the new concept, Euler circuit, if and only if each vertex has even degree. Suppose we have a connected multigraph. If we say that is an Euler circuit, then if and only if each vertex has even degree. This is a necessary condition. Theorem. What is the second theorem? That is, a connected multigraph has an Euler path. When we say that a connected multigraph having Euler path, if and only if it has exactly two vertices of odd degree. Now, this is the definition of Euler path and circuits. What is Euler path? What is Euler circuits? Now, an Euler path is a path using every edge of the graph G exactly once. An Euler circuit is an Euler path that returns to its start. Means circuit means we have to come back to the starting point. Okay, that should be Euler path. Then that starting vertex you have to reach again. That is Euler circuit. Now, does this graph have an Euler circuit? You see, this graph has an Euler circuit. No. Why? Now you go back to the theorem. Now, if suppose you have a Euler circuit in a graph, if and only if each vertex has even degree. This is very important. Each vertex has even degree, then we can say in that graph we have Euler circuit. Now you see here what is the degree? 1, 2, 3. Here 3, here 2, 3, here 1, 2, 3, 4, 5. So there is no chance to get an Euler circuit, because if you have Euler circuit in a graph, then each vertex has even degree, but here all are odd degree. Okay, now see this example. This is the graph. Here what is the Euler path? Euler path means Euler path is a path using every edge of the graph G exactly once. You have to see, you have to write a path. This is a path. Path means you write the vertices. What are adjacent? You can write next, which means D. For example, I am drawing here D, E, B, C. You see, I am not repeating the edge. That is important. That is Euler path. Then A, then B, then D, then C, then E. This is Euler path. You can write a vertex again, but you cannot repeat the edge. That is Euler path. Another condition is a connected multigraph has an Euler path. What is the condition? If and only if it has exactly two vertices or degree. Now you see here the degree of the vertex A is 2, here degree is 4, here degree is 3, here degree is 3, here degree is 4. Now you see this is even number, this is even number, this is even number, here this is odd number, this is odd number. Now you see the theorem. If you have Euler path, if and only if it has exactly two vertices of odd degree. Yes, we have two vertices, means D and E, only two vertices having odd degree. That is, the degree is 3. That's why here we have Euler path. Now see this graph, what we are going to find here, Euler circuit. Now you see D, E, B. For example, I am drawing D, E, B, C, A, B, D, C, E, F, D. Starting point is D. Again, last terminal is also D. So this is an Euler circuit. And one more condition, you see this theorem. If you have Euler circuit, if and only if each vertex has even degree. Yes, we have even degree. Now you see 2, 4, 4, 2, 4, 4. So all the vertices of even degree, and at the same time no edge is repeated in the path, and we are reaching the starting point D in the last D, because a starting point D, last point means starting vertex is D, again last vertex is D, which means it's a cycle, it is a circuit. Therefore this is a Euler circuit. Next we see one more example. Yes, now you see what is Eulerian graph. What is Eulerian graph? An Eulerian graph is a graph containing an Eulerian circuit or cycle. When we say a graph is Eulerian graph, if we have one Eulerian cycle, Eulerian circuit in that graph, then the graph is called Eulerian graph. Now you see the example. We have two graphs. Okay. The first one is Eulerian graph. Okay. Second one is not Eulerian. Okay. We will see. Eulerian graph. Eulerian graph means which has Eulerian circuit. Now, what is the condition for Eulerian circuit? Now you see, for Eulerian circuit, if only if each vertex has even degree. Now, here 2, 2, 4, 2, 4, 2, 2. So in this graph, I can find an Eulerian cycle. That's why this is called Eulerian graph. Why? How is it possible to find Eulerian cycle? Yes, it is possible because all the vertices having even degree. That's why we are telling this is an Eulerian graph. Now you see this. This is not Eulerian. This is not Eulerian. The graph B is not Eulerian. Why? Because here what is the degree? 3. Here what is the degree? 3, 3, 3. But what is the condition for Eulerian cycle or Eulerian circuit? Each vertex has even degree, but here no. This also 3, this also 3, this also 3. Therefore, no Eulerian circuit is existing in this graph. Therefore, it is not Eulerian graph. Now, you see one more example. Which of the following graphs has an Euler circuit? Now, first one is yes. Second one is no. Third one is no. Why? Now, you see again, this is the degree. What is the vertex A? This is the degree 2 vertex. This is degree 2 vertex. This is degree 4 vertex. This is degree 2 vertex. This is degree 2. Yes, all the vertices having even degree, maybe 2, 4, 6, 8, doesn't matter, even degree. That's why here I can write Euler circuit. If any graph having Euler circuit, then that is Euler graph. So which of the following graph has an Euler circuit? This has Euler circuit. The circuit or cycle is here written. A, E, for example, A, E, C, D, then again E, then B, then A. This is Eulerian circuit. Now you see starting point A, again we are reaching that the end. Okay, so this is Eulerian circuit. Now here no, you cannot. Why? This is degree 3, degree 3, degree 4, degree 3, degree 3. So you cannot find Eulerian circuit because every vertex be having even degree, but here it is having odd degree also. Here odd degree, 3, 3. Same 1, 2, 3. Here degree 3. So it's not possible to find Eulerian circuit. That's why only in the first graph we can find Euler circuit. That's it. Thank you.